Welcome, everyone. This is Celia Merzbacher. I'm Executive Director of the Quantum Economic Development Consortium, or QED-C, as I think you all know. This is the next in a lecture series, and I'll let you hear more about that from Eric Imhoff in just a moment. But I wanted to welcome everyone and let you know how much the leadership of QED-C appreciates the Quantum for National Security tax arranging for this series. It's, I think, going to be a highlight of 2024, frankly. It's filling a much needed gap, clearly, based on the enthusiastic response that we're getting. So we're always looking for feedback. Feel free to send your recommendations for future such programs or lectures that you think would be good to add, or any other comments on how QED-C can kind of help fill the quantum gaps in your position from where you're sitting. So without further ado, I'll send it over to Eric to introduce our speaker and tell you a little bit more about the program. Eric, over to you.
Thank you, Celia. So welcome back, everyone. This is the Quantum for National Security TAC lecture series. We are now, I believe this is the 5th talk out of 10, so we're reaching the midpoint. Now, as a reminder, the goal of this series is that the Q4NS TAC, Quantum for National Security, we have a lot of people that want to contribute to the national security conversation about how quantum systems can be used. But the members of our TAC have a wide background range. So we have some very deep technical individuals, as well as business people, diplomatic people, and people that focus on the law side. And we're trying to give everybody a common understanding of the quantum technologies that are going to be realistic to talk about in the near term. And so my background is quantum sensors. I was putting together this list of what I see as the 4 big types of quantum sensors to pay attention to in the time that I'm going to be chairman. And I'm hoping that the future leadership of the TAC will continue this idea and talk about other quantum technologies. So as Celia said, if there are things that you would like to talk about as a TAC, please do reach out to me and Charlie, and we will try to make that happen. But for today, this is a members only talk. Some of the talks are reserved as a benefit for being a member of QED-C, while others are meant to be public webinars to drive new membership interest. So this is a members only talk. It will be recorded and made available via the QED-C website. Please do not share the video outside your organization. And for today, there will be a Q&A session at the end. You're free to use any of the information you received during this lecture in the Q&A, but do not reveal any speakers or affiliation or make any attributions for how you got that information. So with that being said, today we're going to be hearing from Dr. James Camparo, who's following up last week's talk on atomic clocks from Dr. Stephen Jeffords. So Dr. Camparo is a PhD in chemical physics from Columbia and now an aerospace fellow at the Aerospace Corporation's Physical Sciences Laboratories, as well as an adjunct professor from Whittier College. And he has research interests in the development of laser-pumped atomic clocks, the study of atomic timekeeping aboard spacecraft, experiments investigating the atom field interaction, and collaborating with his wife, who's also a Whittier professor in social science statistics. So with that, if you do have questions over the course of the talk, please either put them in the chat or raise your hand, and I will do my best to pose them to Dr. Camparo after he has concluded. So with that, James, I'm going to stop sharing my screen and hand it over to you.
Okay, so I'm going to share my screen now. And first of all, can everybody see the screen and everything's okay?
Everything's great and we can hear you.
Perfect. All right, well, I really want to thank the organizers for giving me this opportunity to talk about atomic timekeeping in space and to, let's see if this is going to, oh, how do I, there we go. Okay. To give you a roadmap of where we're going, I'd like to just talk about very briefly the overview of space system timekeeping, then a brief history of atomic clocks in space, and address the question of why would you want to employ atomic clocks in space when crystal oscillators have or can have incredibly low phase noise. Then talk about time creeping across the space enterprise and some of the issues you have to worry about. And after that, move into the the atomic clocks we're presently using in space systems, and then what we're thinking about for near-term next generation atomic clocks in space. Okay, so overview of space system timekeeping. So this figure gives you a sense of what are the kind of things we think about. So there's going to be a ground station, and in the ground station, you're probably going to employ atomic clocks for very good timekeeping. You're not going to be too worried about the size, weight, and power, the swap of that, because so long as it's rack mountable, it's fine. Then there's going to be uplink, downlink synchronization to the in-view satellite, maybe cross-link synchronization out of view satellites. And these would be to, let's say, high Earth orbit, larger satellites, and with the larger satellites, they can carry larger atomic clocks where you're talking maybe about 50 watts, 10 kilograms. And the issue here is going to be on longevity and reliability. Because these are larger, more expensive satellites, they're going to have a longer mission life. They may be using crosslinks to synchronize low Earth orbit satellites, smaller satellites that maybe are CubeSats, and here you're talking about swaps on the order of maybe 5 watts and half a kilogram. And again, you want modest longevity and reliability, but that may not be the great driver because these low Earth orbit satellites, smaller ones, would be thought to be replenishable. And then, of course, there are going to be users on the ground that are going to have their own clock. Now, one area where precise timekeeping comes into play is global navigation satellite systems like GPS. So to illustrate what's going on there, imagine this two-dimensional positioning problem. You've got a receiver on the ground in the car, and they're receiving signals from satellites in the sky. The signals from the satellites carry information on the location of the satellite. So in this case, the X and Y coordinates of those satellites. The receiver is trying to figure out its location, its X and Y coordinates. And it knows the signal coming down from the satellite has information on when the signal left the satellite. The receiver clocks the arrival time. And since you know the travel time of the signal, and its speed, the speed of light, then you can figure out the range. If you can figure out the range, you can set up these propagation equations. And there are really three things the receiver on the ground doesn't know. It doesn't know its X coordinate. It doesn't know its Y coordinate. And because the speed of light is like 700 million miles per second or a foot per nanosecond, you really need to keep accurate time if you're going to try to clock the travel time of that signal. So the receiver clock really doesn't know its time error with respect to truth. So there are three unknowns. You need three equations, which means you need three signals from three satellites. And hopefully these are widely spaced in the sky so that these signals are orthogonal. And you can solve the equation for propagation. Now, as I said, the speed of light is a foot per nanosecond. So if you're going to try to measure your locations within 30 feet, 10 meters roughly, then you need to keep time at the nanosecond level. The other place that precise timekeeping comes in is in spread spectrum communications. And there, what you've got is you are going to hop your carrier frequency around in some pseudo-random fashion in some range of carrier frequencies. Now, what that buys you is, number one, because you're hopping your carrier frequency around in a pseudo-random fashion, you've essentially encrypted your communication. Moreover, because any jammer doesn't know where the carrier frequency actually is at any moment of time, they have to spread their jamming power over the full range of carrier frequencies where you might be, which reduces the ability of any jammer to interfere with your signals. And if you think of different users as interferers with each other, then because you're doing this frequency out spread spectrum, you've increased this channel of carrier frequencies to handle more users. You've increased the channel's capacity, because so long as one user is not hopping to the same carrier frequency as some other users, they can all use this same range of carrier frequencies. Now, in order to do this in general, and I'm speaking just order of magnitude here, you're talking about keeping time at roughly the microsecond level. And you might think, well, geez, if you can keep time at the nanosecond level for global navigation satellite systems, then certainly you can keep time at the microsecond level for comm. But in GNSS, we work very hard to keep that nanosecond type of synchronization. So you get updates from the ground to the constellation either every day, or in the case of Galileo, which is a European GNSS system, you're talking about updating the constellation every 90 minutes. In communication systems, we'd like to go longer, like days and weeks, maybe even longer than that, before we have to do an update to the constellation. And keeping time at the microsecond level for weeks is a hard problem. To put some of these numbers, I said nanosecond level timekeeping and microsecond level timekeeping in perspective. I'm going to do this. I like to watch my hands move around as I talk. You can get that from my last name, maybe. To put those numbers into perspective, as I said, in GNSS, we figure out the range by the signal travel time. We are looking to keep time at, let's say, the 30 nanosecond level over 24 hours in the case of GPS. That's equivalent to trying to measure the Earth-Moon distance to the diameter of a human hair. With regard to communications, we're trying to keep time at the microsecond level over periods of, let's say, a week or more. That's equivalent to trying to tag the location of a bacterium on the Afghanistan-Pakistan border. I think that kind of intuitive contrast gives a better appreciation for the numbers we're dealing with in timekeeping in space. Now, Steve went over a diagram like this in his past lecture, and just to remind everybody, this is the sort of block diagram of a generic, what's called passive atomic frequency standard. You start out with a voltage-controlled crystal oscillator, VCXO, and that's outputting about 5 to 10 megahertz. And that's providing, that frequency is providing the tick rate for your clock in order to keep precise time. You take the output of that VCXO, and then you frequency modulate it at a low rate, let's say 100 hertz, 150 hertz, 200 hertz, something like that. And then you multiply that up into the microwave regime, where it can cause an atom to jump rungs on its energy ladder diagram. Now, atoms have a very high Q for the absorption of microwaves, which means that they can distinguish between very slight variations of that microwave frequency. So we detect the atom's response to the microwave, because we frequency modulated it, using phase-sensitive detection. And the output of that phase-sensitive detection gives you that red curve that you see up in the upper right portion of the figure. Excuse me. So you'll notice that can you see my pointer by any chance? I don't think so. Can you see my pointer?
Yes, yes, I can. Can you move it around again? Yeah, I can see that. When you're moving it, I can see it.
All right, good. So if this VCXO is outputting a frequency that after it's multiplied is below the atomic resonance, you'll generate a positive voltage, which you feed back and drive the VCXO frequency forward. If you overshoot, you'll generate a negative voltage, which drives you back. So in this way, you lock the frequency of that VCXO to the atomic resonance, in a very real sense, transferring the stability of atomic structure itself to the output frequency of this voltage-controlled crystal oscillator, and hence the tick rate of your clock. Excuse me. Now, Steve also went through this diagram. It's called the Allen deviation diagram. We measure the random fluctuations in this frequency using an Allen deviation statistic. And for those of you who feel very comfortable with statistics, the Allen deviation is cousin to what's called the standard error in traditional statistics. And we measure the Allen deviation in terms of fractional frequency. That is the frequency variance divided by the nominal frequency. And it basically gives you how many significant figures are we seeing that frequency fluctuate at. So if the Allen deviation number falls like the square root of the averaging time, the time at which you average the signal, then the noise process driving those fluctuations is wave frequency noise. If the Allen deviation is a constant as a function of the averaging time, then the noise process driving those fluctuations is flicker frequency noise, having a power spectral density of 1 over S. If the Allen deviation rises like the square root of the averaging time, then over those time scales, the random process driving the fluctuations is random walk frequency noise. So the Allen deviation is really telling you two things. The magnitude is telling you something about the size of those frequency fluctuations. At what significant difference are they occurring? So for a part in 10 to the 11th, you're saying that out at the 11th significant digit, you're seeing fluctuations in the frequency. And its behavior as a function of averaging time is telling you something about the noise process driving those fluctuations. And you can see a reference here to get more information on it. Okay, how did we get to atomic clocks in space? The first mention of an atomic clock at all goes back to a lecture given by Isidore Rabi, who won the Nobel Prize in 1944. He was giving what's called the Rickmeyer Lecture, given out by the Association for Atomic Physics. I'm not sorry, the American Association for Physics Teachers, AAPT. Anyway, he was giving his lecture, and there are no notes on this lecture. We have no slides or charts from this lecture, but there was a reporter from the New York Times at this lecture who reported in the New York Times that during the lecture, Rabi made the point that you could use atoms to stabilize the frequency of a crystal oscillator, and in that way create a quantum or atomic clock. 11 years later, we see, it's 11, 10, something like that. The first atomic clock was developed at the National Physical Laboratory in England by Jack Perry and Louis Essen, and this is based on a beam of cesium atoms moving down a tube that they used as their atomic source. And they used this atomic clock to calibrate crystal oscillator clocks. This was then quickly duplicated in the United States by Mockler at the National Bureau of Standards, the predecessor to the National Institute, of Standards and Technology. It was soon after that that we came to portable atomic clocks. In 1956, the first portable atomic clock, you see a picture of it here, called the Atomicron. This too was based on a beam of cesium atoms moving down a tube that had an accuracy of a part in 10 to the 10th. 11 years later, we see something that you truly might call a portable atomic clock being carried off a plane. This was a rubidium atomic clock developed by General Technology Corporation. It was based on rubidium atoms in a vapor, 14 kilograms, 15 liter with an 8-hour battery life, and a short-term Allen deviation, wave frequency noise, of 5 parts in 10 to the 11th per root tau. In 1973, the United States Navy and the United States Air Force decided to combine their satellite navigation programs into what was to become the Navstar GPS program. And as part of that, in 1974, they launched the first atomic clocks in space to see how timekeeping could be maintained by atomic clocks in space. Here you see on the right a picture of a commercial version of it, the atomic clock that they launched. It was built by a company that was located in Irvine, California called Effertom. It was a rubidium atomic clock based on a vapor of rubidium atoms, 1.3 kilograms, 1.2 liters, 13 watts, with a short-term Allen deviation of 1.3 parts in 10 to the 11th. Again, wave frequency noise we're talking about. The thing to take from this is that all talk of atomic clocks in space and I would even argue quantum devices in space, go back to this first launch of these rubidium atomic clocks on the NTS-1 satellite in 1974. This is a picture of the evolution of rubidium atomic clocks used in the GPS program. We see the GPS-2A rubidium atomic clock. It was really a modified version of that commercial Effertom clock. Then in the 80s, Bill Riley at Perkin-Elmer did a major redesign of the rubidium atomic clock and achieved unprecedented performance capabilities out of the clock. This became the GPS-2R rubidium atomic clock. And then you see the GPS-2F and GPS-3 atomic clock, now with a short-term stability of 8 parts in 10 to the 13th per root tau. And as these atomic clocks improved, so you would imagine the size, weight, and power went up. So why would you think about employing atomic clocks in space? This is a question that often comes up. Well, here's a power spectral density plot of a commercial, high-quality quartz crystal oscillator, 1 watt, 1 liter, 0.7 kilograms, 15 watts, warm-up, 4 watts steady state. And what you see for this high-performance version is at 10 hertz off the carrier, you're talking about 150 dBc. That's really great. So why not use these crystal oscillator clocks? Why go to atomic clocks at all? Well, one issue is long-term timekeeping. This chart on the right shows the Allen deviation of that high quality uncontrolled crystal oscillator compared to the Allen deviation of a GPS-2F rubidium atomic clock. And what you see is that the frequency fluctuations after about, 15 minutes become much larger than what you see in the GPS rubidium atomic clock. So even though the high quality OCXO may have real advantages in terms of size, weight, and power, when it comes to long-term timekeeping, the atomic clocks have much better capabilities. And in space systems, you're talking about updating your constellation, your satellites, every hour, every 10 hours, every day, every week, something like that, where long-term is really important. This next chart shows that more clearly, where this is the time error in microseconds that each of these clocks would build up as a function of days after synchronization. And you see that once you start hitting 1 day after synchronization, the difference in timekeeping capability is 3 orders of magnitude. So that's one reason to employ atomic clocks in space. Another reason has to do with space radiation. And we had a great example of this back in 2000 when MILSTAR first went up. MILSTAR stands as an acronym for Military Strategic and Tactical Relay System. And it was decided that for this communication mission, they were going to have to fly atomic clocks. But that decision was made after the first MILSTAR satellite was already in production using crystal oscillator clocks. And so the government decided that they were going to launch Flight 1 with crystal oscillator clocks to test out the communication capabilities of MILSTAR. And then all other satellites would launch with rubidium atomic clocks. And using cross-link synchronization, Flight 1 would always be designated as a slave, tying its time and frequency to the rubidium atomic clocks carried on some other satellite, which would be referred to as the master. Now, in the system, so we have the SMUX, affectionate SMUX, Satellite Mission Control Subsystem, has a cesium atomic clock, which was synchronized to UTC USNO. The in-view satellite was Flight 1. The out-of-view satellite was Flight 2. Flight 1 was slaved to Flight 2 using cross-link information. And the SMUC, the ground station, could see the frequency and time of the Flight 1 clock as it's synchronized to Flight 2. And it could also download telemetry signals. And one of those telemetry signals was the voltage that needed to be applied to the VTXO to keep it tied to the rubidium atomic clock on Flight 2. July 14, 2000, we have one of 2 largest solar flares for that solar cycle. the Bastille Day solar flare. And what you see in gray here is the solar proton flux for protons with an energy greater than 50 MeV. It jumped by 4 orders of magnitude on July 14th. And correlated with that jump, the ground station saw that there was a large jump in the voltage that was controlling that VCXO. And when you work backwards, it indicated that the crystal oscillator had a frequency jump of 2 parts in 10 to the 10th at that time. I wonder if I can do it this way. I can do it that way. Great. Okay. Now, if Flight 1 had not been slave to Flight 2, then the time error buildup that would have occurred is shown by the red triangles here. And you see that just several days after the flare, Flight 1 would have built up hundreds of microseconds of time error. And as I said, in satellite communications, order of magnitude, we're trying to keep time at the microsecond level. So this would have been horrendous. What the user would have actually seen if the ground station had not been doing its required uplinks, which have to be taken out of the data so that it can be unclassified. In any case, what a user would have seen is shown by the gray circles. After weeks, only maybe a microsecond of time error would have built up. This points to the inherent radiation insensitivity of atomic clocks compared to crystal oscillators. And when you're talking about missions that might go through solar max, or you're talking about missions that might have to worry about man-made radiation, I would argue that you are almost required at that point to really think about using atomic clocks in space. Okay, so timekeeping across the space enterprise. This is now another picture of that overall view of space system timekeeping. So we have a ground station having an atomic clock, and maybe it's a cesium clock. There's uplink, downlink synchronization to the in-view satellite, which is rotating. The Earth is also rotating, and the satellite is in orbit at a high altitude relative to the ground control station. One thing to make sure you understand is we talk about better atomic clocks in space, better atomic clocks in space. What we forget often is the better the atomic clock in space, you've got to have a better, even better atomic clock at the ground station. So as we improve atomic clocks in space, we have to keep in mind that we're going to have to be improving atomic clocks at the ground control station. So let's look at this a little more deeply. First of all, there are ground control issues. So the ground control, as I said, has to have better clocks than what we're flying on board the satellite. Additionally, as you're thinking about uplink, downlink synchronization, you have to worry about atmospheric and ionospheric delays. And finally, if you're talking about trying to keep time at nanosecond levels or maybe microsecond levels, you're going to have to worry about multipath, both at the ground control station and probably on board the satellite. So satellite and ground control station design can be important issues. The other thing you can't get rid of and you can't forget is relativity. So one thing to notice is that here's the ground station and the satellite is orbiting. So the satellite is in relative motion relative to the ground. So the ground, looking at that satellite, is going to see the clock ticking more slowly than its own clock. This is called relativistic time dilation, and it's a special relativity effect. The other thing is, as the satellite is cross-link synchronizing to its orbiting neighbor, you have to recognize that the signal, if I'm the satellite behind, the signal I send has to lead the satellite that's in front of me, and the signal that the satellite, both have to lead the satellite. And that means that the signal coming from the front satellite to the back is going to have a shorter propagation time than me sending to the satellite in front of me. And that difference is called the Sagnac effect. It's a relativity effect, but really derives from the fact that the speed of light is finite. And that has to be included as you think about synchronization. Finally, you have to recognize that the ground station clock and the satellite clock are at different places in the Earth's gravitational potential well. This is called the gravitational redshift. And speaking prosaically, it comes to the fact that gravity slows the flow of time. So clocks on the Earth tick more slowly than clocks in space. To give a sense of what the numbers are that we're dealing with, at least in the relativity effects, let's think about GPS. Here we've got a satellite in orbit about the Earth at about 12,000 miles, and it's moving at about 2.4 miles per second. So the first effect is this gravitational redshift effect. If you didn't account for that, then the satellite clock would build up a time error relative to the ground station of 45 microseconds every day. We're trying to keep time at 30 nanoseconds in GNSS systems. That's 3 orders of magnitude larger than what we're worried about. The second effect is that the satellite is moving relative to the ground station clock. This gives rise to what's called the second order Doppler shift, or that time dilation effect. And if you didn't account for this, you would build up about 5 microseconds every day. Again, about 3 orders of magnitude larger than what we're looking at. And finally, we have to recognize that the satellite is not in a circular orbit. The difference for the GPS is about 300 miles between apogee and perigee. And what that means is that the satellite clock is coming into and out of the Earth's gravitational potential well. So twice a day, there is a change in the clock's timekeeping that amounts to an amplitude of about 50 nanoseconds. Again, that has to be included in the timekeeping of the system to get to our nanosecond level timekeepings we need for GPS. Okay, what about the atomic clocks we're presently using today? Well, I know Steve went over some of this. I want to go over it a little bit more, and maybe in a little bit more detail, because it'll help understand why we're moving to the next generation of atomic clocks. I would argue that the rubidium vapor cell atomic clock is probably the workhorse of precise timekeeping in space today. The physics package of that clock is illustrated here. It consists of a rubidium discharge lamp, a filter cell containing one isotope of rubidium, rubidium-85, a resonance cell containing the other natural occurring isotope of rubidium, rubidium-87, sitting inside a microwave cavity tuned to 6.8 gigahertz, and a photodiode. Now, in the RF discharge lamp, you basically use that discharge to excite the rubidium atoms way high up their energy ladder, and when they fall down, they emit spectral lines. Now, 2 of those lines will correspond to the excited state falling down to 2 hyperfinely spaced rungs of the atom's ground state, where the electron is orbiting the nucleus as close as it can get. If you look very finely, you would see that that energy has 2 hyperfinely spaced rungs, called in this figure the F equals 2 hyperfine rung and the F equals 1 hyperfine rung. Due to a coincidence of nature, when these spectral lines pass into the filter cell, one of them can be absorbed, allowing the other one to pass through into the resonance cell. Now that's important because the energy level spacing between those 2 hyperfinely spaced rungs is 30 micro electron volts. Gas kinetic collisions in the vapor have an energy of 30 milli electron volts, 1,000 times more energetic, which means if you were to take a snapshot of the atoms in this vapor at any moment of time, because of these collisions, half of them would be on the F equals 2 rung, and half of them would be on the F equals 1 rung. Now, there's a law in quantum mechanics related to how quantum systems interact with electromagnetic radiation that says that there can be no net absorption of an electromagnetic field without a population imbalance between the 2 rungs of the energy ladder that you're trying to connect with that electromagnetic field. Well, here there's no population imbalance, so there could be no net absorption of microwaves with this system as it is. But look at what that line from the lamp is essentially tuned to. It can excite atoms out of that F equals 1 rung to the excited state. So the atoms from the F equals 1 rung get thrown up into the excited state, and then they fall down. And they can fall down into either the F equals 2 rung or the F equals 1 rung. If they fall into the F equals 1 rung, they get thrown up by that light from the lamp to the excited state, and they can fall down into the F equals 2 rung or the F equals 1 rung. And you see in this process we're pumping, optically pumping, atoms from the F equals 1 rung into the F equals 2 rung. Now, with few atoms in the F equals, and this process of optical pumping only takes a millisecond or two. That with few atoms in that absorbing rung, well, there's nothing to attenuate the lamplight passing through the rubidium vapor after that optical pumping comes into equilibrium. And so we have a high level of light hitting the photodetector, producing a high voltage. If we apply microwaves at the exact right frequency, 6834.7 megahertz, we can make atoms return to the absorbing state. With atoms returning to the absorbing state, there is a dip in the transmitted light intensity, and we can use that dip in a feedback loop to lock the VCXO frequency that's generating that 6.8 gigahertz to this atomic resonance in the rubidium vapor. So one thing you see that's going on is that the lamp is not only preparing the atoms for the absorption of microwaves through this optical pumping process, it is also monitoring the atom's absorption of those microwaves. The lamp is also doing something else. Due to quantum mechanics and the interaction of quantum systems with electromagnetic radiation, the lamp actually perturbs the energy level spacing to make it shift around. This is called the AC stark shift or the light shift effect, and it's qualitatively relatively simple to understand. Just imagine an atom as a dielectric using classical E&M. Imagine the atom as a dielectric. So you got a positive charge in the center, and this is surrounded by an electric cloud. Turn on an electric field. You induce a dipole moment in the atom. And we know from classical E&M, the dipole moment is going to be proportional to the electric field, and that proportionality constant is called the polarizability. In this case, the polarizability of the atom itself. It will be frequency dependent because we're talking about an oscillating electric field. We also know from classical E&M that an electric dipole will have an interaction energy with an electric field. So in second order, that induced dipole moment interacts with the electric field that produced it, and that interaction energy acts as a perturbation on the atom, shifting the atom's energy level spacing. And if there's a shift in the energy level spacing of the atom, there will be a shift in the clock frequency that VCXO is locked to. Now that shift in frequency is classical in E&M. It's the dipole moment times the electric field, but the dipole moment is just alpha E, so that the shift is proportional to the electric field squared or the light intensity. And so the light shift, the clock frequency, depends on lamp intensity linearly. If the lamp intensity changes, the clock frequency changes. Now you might be thinking, oh, that's all very nice. That's quantum mechanics. What does it have to do with real systems? Well, what you see on the right is on-orbit data from GPS Space Vehicle number 54. Two things are shown. The lower gray diamonds are the frequency that was measured by ground control stations for this satellite clock. The dark diamonds, shown as the upper figure, are telemetry coming down from the satellite indicating the DC light level hitting that photodetector in the clock. And what you notice is that 200 days after turn on, there were 5 jumps in that DC light level. And correlated with those jumps in DC light were 5 jumps in clock frequency. The light shift effect manifested on orbit in GPS. Now, these jumps were not so large that they caused any problem to users, but we do now know that these jumps, at least for GPS Block 2R, and quite likely for GPS Block 2F and 3, and quite likely for all rubidium atomic clocks in orbit, that includes Beidou, that includes Galileo, that includes Milstar and Advanced DHF, that these jumps in lamplight, inducing jumps in clock frequency, are what are driving the random walk frequency noise in the clock, and that's driving, or that's contributing to what's called the GPS signal and space user range error. which is the fundamental locational capability of any GNS system. It consists of two terms. The signal and space user range error is dominated by two terms: the error of the clock on board the satellite and the ephemeris error. And here we're saying that the clock's contribution to the signal and space user range error is being driven by these AC start shift effects. Okay, another clock that you hear talked about in space systems is a cesium atomic clock. You start off with a cesium oven, it goes to an and the atoms in those two hyperfine levels, same number, it goes to an inhomogeneous magnetic field. Atoms that find themselves in one of these hyperfinely spaced rungs are thrown away, allowing atoms in the other to pass through a separated field microwave cavity. I won't talk about why you use that. It just gives you a slightly higher Q. If the atoms absorb the microwaves, they jump rungs so that when they pass through a second inhomogeneous magnetic field, they can be focused onto a hot wire ionizer, giving you an electrical current that you can feed back and lock the voltage-controlled crystal oscillator to the cesium atoms in this beam. You also hear about hydrogen masers. There, you take hydrogen atoms, they're in the two hyperfinely spaced rungs, you pass them through an inhomogeneous magnetic field so that only atoms in one rung pass into a high Q microwave cavity where the atoms undergo gain, producing a microwave field of very, very narrow bandwidth that is picked up, and using a phase lock loop, you lock the frequency of a crystal oscillator to this microwave frequency coming out of the maser, generating an atomic clock signal for yourself. There's also something called the passive hydrogen maser. In the passive hydrogen maser, you use the gain medium almost as really an amplifier, a narrowband amplifier. So you start out with your quartz crystal oscillator, 510 megahertz, you multiply it up to 1.4 gigahertz, you inject it into your microwave cavity where it can interact with the hydrogen atoms. And if it's of the right frequency, you'll get a maximum gain, which you sense with a pickup loop, and use that to lock the quartz crystal oscillator to the hydrogen resonance now for your clock signal. This chart is on the left, gives you the Allen deviation of these atomic clocks. In the upper right, you see time error buildup as both log-log plot, time since synchronization. And what you notice is that the present-day space-qualified cesium beam clocks really are not that good compared to the rubidium vapor cell clock we're flying on GPS, passive hydrogen masers, and even active hydrogen masers. I also point out that after you start, once you're worried about, let's say, time error buildup, once you're worried about synchronizing your constellation, let's say 10 hours or longer, the rubidium clock is just as good as every other one, maybe even a little bit better in some cases. But look at the size, weight, and power. The rubidium vapor cell clock is 6 liters, 7 kilograms, 30 watts. The size, weight, and power is unbeatable, and its performance is really excellent. This is why I say the rubidium vapor cell clock today is the workhorse of atomic timekeeping in space. Very good stability and very low swap compared to your other choices. Okay, what about the future? And I talk about near-term advanced space clocks. And when I say near-term, I'm saying something that one could imagine being operational within the next 10 years. If you look at the literature and you read things, everybody and their brother is going to say, we're working on an advanced clock. Okay, but when will it be ready for space? I'm talking here about things one can reasonably expect you could actually put in an upper effort, you could be operational within the next decade. One is the pulsed optically pumped rubidium atomic frequency standard, pioneered by researchers at the Italian government's equivalent to our NIST, it's called INRIN, Istituto Nazionale di Ricerca Meteorologica. I love saying that. So basically what they did is they said, look, let's get rid of the RF discharge lamp and we will replace it with a pulsed diode laser. So you pulse in this lower diagram here, you pulse the laser on and you allow it to do this optical pumping for you. Then you turn the light off and you apply 2 microwave pulses called Rabi pulses separated by what's called a Ramsey period. Again, I'm not going to talk about why. It gives you a slightly higher Q for your atomic signal. In any case, after the second microwave pulse, you turn the laser back on to see, did the atoms absorb the microwave? Now, the advantage to this is you're probing the atom with microwaves when the light is not present. So there is no AC stark shift effect. There's no light shift effect. It goes away. The Leonardo SPA is developing a flight version of this for a test demonstration on Galileo, 17 liters, 18 kilograms, 30 watts. They've presented engineering model data. It looks unbelievably good, and there's a lot of international interest in this technology. In the United States, Frequency Electronics Incorporated is under Navy contract to build a version of this, not necessarily for space. And we at the Aerospace Corporation are working on a space version of this clock as well. Now, another near-term clock for space is JPL's Deep Space Atomic Clock called the DSAC. This is based on mercury ions. So what they do here is they take a sample of 199 mercury ions, and because they're ions, you can control them with RF electric fields. And due to a coincidence of nature, these 199 mercury ions can be optically pumped by light from a 202 mercury ion lamp. Now you're having to use 194 nanometer light to do this optical pumping for you, and that's why they have to use a lamp rather than any kind of laser at the present time. After the optical pumping happens, you shuttle the atoms into what's called a 16-pole trap. That gives them some better long-term performance. I won't go into why. And you expose them at that point to 40.5 gigahertz microwaves. You shuttle them out and use the lamplight to see, did the atoms absorb the microwaves? And then in that, create a feedback loop to lock their ultra-stable oscillator to this atomic resonance in the mercury 199 ion. JTL built a flight version of this, 18 liters, 16 kilograms, 45 watts. This was launched already on the Orbital Testbed satellite in 2019. It operated for 18 months, and the performance was really, really good. And again, there's a lot of international interest in this technology for space. And finally, you'll hear talk of optical clocks for space, and these are either going to be based on rubidium vapor or a vapor of iodine molecules. And the idea is you're using a pulsed laser here. And the pulses are on the order of femtoseconds, 10 to the minus 15 seconds. And there's a pulse repetition period on the order of 10 nanoseconds. Now, you know that if you take a pulse train like this and you look in the Fourier regime, you're going to get a comb of Fourier modes. Fourier times, they're often called. And the mode spacing is related to the pulse repetition period, and that's related to the cavity length in the pulse laser. And as the cavity length changes, the mode spacing will change. Also, due to the fact that the phase velocity and the group velocity in the active medium are not necessarily the same, there's something called a carrier envelope offset. In other words, if this is 0 and this is my cone line, it's offset from 0 by some certain amount. Now that phase velocity and group velocity relationship can change randomly. So the cone, not only are the modes changing, but the carrier envelope offset is changing. So the modes are doing this. Terrible for a precise clock. But because this is femtosecond pulses, the spread, that Fourier spread is very large. It's not spanning. It spans from the red to the blue. So think about taking one of these red modes. Well, what's its frequency? Its frequency is some integer n times the repetition frequency, which is the mode spacing, plus the carrier envelope offset. Double it. And this is what you get. Now that is going to be a mode now in the blue, which you can beat against a blue mode, whose frequency also is some integer n equal to 2m plus the carrier envelope offset. That beat is the carrier envelope offset frequency. And if I can measure the carrier envelope offset frequency, I can stabilize the carrier envelope offset frequency. So I can stabilize this offset, let's say, to the mode spacing. So now the cone is doing this. Down, low, high, low, high, low, high. If I now lock one of these modes to an atomic resonance or a quantum resonance, either a 2-photon resonance in a rubidium vapor or a rotational vibrational transition in the iodine molecule, then the whole comb is locked and the tick rate for my clock becomes the repetition rate of my pulses on a photodetector. There's AFRL, Inflection, Vector Atomics have all done work on this technology. And again, there's very strong international interest. The swap estimate for this for space that I have seen is 30 liters, 13 kilograms, and 90 watts. The next chart, finally, I need to get to the CPT, Coherent Population Trapping Clock, for chip scale clocks. This is a simple design. You start off with a diode laser, which you can modulate the injection current, and for VCSELs, you can modulate it at very high rates, up into the gigahertz. So if I modulate the injection current at 3.4 gigahertz, I'm going to put sidebands on the carrier. Now, that sideband here can be like 6.8 gigahertz. And that means what? Well, it means that one mode, one sideband, can excite atoms out of the, for rubidium-87, out of the F=2 rung of the atom. And the other sideband can excite atoms out of the F=1 rung of the ladder. Now, in quantum mechanics, you don't think so much about probability, but rather amplitude for an event to occur. And the probability is the amplitude of that event occurring squared. And that's what you have to worry about in quantum mechanics. And this is a quantum mechanical system. So when I have both of these paths for excitation operative, the probability for the atom to get excited, get into that excited state, the probability is the amplitude for path 1 plus the amplitude for path 2 squared. Well, notice if you square it, there's an interference term here. And it just so happens that the amplitude for path 1 has 180 degree phase shift compared to the amplitude for path 2. That means when these two sidebands are exactly on resonance together, then the probability of excitation is 0. The atom does not absorb the light. There's an increase in the transmitted intensity, which has a very high Q, which I can use in a feedback loop to lock the frequency that's generating this injection current modulation to the atomic resonance in the atom, giving me my tick rate. The advantages of this is you're no longer limited by microwave cavities. It allows you to get to very small designs. And in cost space CTEX, you're talking about 120 milliwatts, 35 grams, and what 16 milliliters. And here you see a picture compared to a US quarter. Okay, this is an Allen deviation plot of the performance. You see the dashed line is the GPS-3 clock specification. The GPS-3 RAP meets the specification with margin, and both the AFRL ORAP, the optical rubidium atomic frequency standard, the JPL mercury ion, and the in-rim pop clock all have better performance than what we're flying in space today. Clearly, the chip scale atomic clock doesn't. When you go small, you sacrifice performance. That's almost the rule of engineering. But what I want to point out is that for the JPL mercury ion clock and the in-rim pop clock, the Allen deviation is so small that the timekeeping error is now basically so small that you've taken it out of the GPS signal in Space User Ranger. And that's important to remember because there's no point in improving GPS clocks beyond this level because you've already taken the clock out of the signal in Space User Ranger. You're limited by the ephemeris error, and until you improve that, there's no reason to improve clocks in space beyond this level. I also will point out that there's a lot of active research looking to improve chip-scale atomic clocks so that these would eventually drop into the in-rim pop and mercury ion clock development areas. Looking to the future, we have to recognize that we're going to have to be synchronizing clocks on the moon and in cislunar orbit to clocks that we have on Earth. The Earth-Moon travel time is about 2.5 seconds. That's going to impact our ability to synchronize lunar clocks to the Earth. We also have to start thinking in terms of what's coming in the inner solar system. We're going to have clocks and systems in Mars and in Martian orbit. And that all those clocks on Mars, on the Moon, on the Earth, are all going to have to be synchronized in some fashion. And it's important there to recognize that the round-trip travel time from Earth to Mars can be anywhere from 6 to 45 minutes. How is all this going to work? People are actively thinking about this today, and also thinking about how relativity comes into all of this at a very complicated level. So with that, let me thank you for your attention and open it up to any questions you might have.
Well, first of all, James, thank you very much. That was a fantastic talk. We do have some questions in the chat here, and just as a reminder to everyone online, if you have a question, please type it into the chat here, and I'll do my best to answer or to pose it to James. So I'm just going to go down the list here in no particular order, just in terms of when these questions arrived. So I have a question here from Ben who says, can you explain in simple terms how to understand the square root dependence on tau?
Oh, yeah. You know that, let's say you have 1,000 resistors, and those resistances, you measure the resistance of each resistor, and it's some value, and there's some random variation. So you calculate what's my mean resistance. Okay, but you'd like to know what's my uncertainty in that mean resistance. Well, the uncertainty in the mean resistance you calculate goes like, or decreases like, the square root of the number of resistors you're working with. So if you work with 10,000 resistors as opposed to 100 resistors, your uncertainty in the mean value of the resistor is 10 times smaller. So the uncertainty in any mean value drops like the square root. If I average for 100 times longer, my uncertainty in the mean value of the frequency will drop by the square root of 100. Does that intuitively, is that a better intuitive explanation of the square root?
It certainly makes sense to me, and and Ben says in the chat, yes, with an exclamation point. So great. Thank you, Ben. We've got a question, a handful of questions from Matthew. I'm not sure we'll be able to get through all of them, but we'll try. So he says, thank you for the stellar presentation. Question 1, in the high frequency trading, how far away do you believe we are from executing synchronized trades in multiple financial exchanges using atomic clocks, or are we doing that now?
This is way out of my area of expertise. I think the numbers I've seen are that on financial trading, it again gets into the microsecond regime. But I thought I saw numbers where they were trying to get, or they thought that they were going to need hundreds of nanoseconds. But I would have to refer you to the literature on that more than my scanty remembrance. I apologize.
No worries. He asks if it matters what type of atoms you use, and says example, rubidium versus cesium. And I think you were able to speak to that a little bit with the many different types of clocks that you showed and the different performance that they had. So I'm just going to try to filter these a little bit for the time frame we've got. So does the atomic chemical composition impact the application or accuracy? What drives the type of atom selection?
I think it comes down to the engineering of the full package. So clearly you want an atomic clock and an atom that has a very narrow, very sharp resonance, a very high Q. Well, that's going to mean that you can lock very tightly. But you pay a price on that. If I have a very, very narrow Q, if my VCXO for some reason, let's say for radiation, jumps out of the capture band, well, now my clock has to undergo a search mechanism to bring it back. If I have a very wide resonance, I have a very wide capture range, so I can tolerate larger jumps of my VCXO. So I think it comes down to an engineering question in what are you concerned about from the application point of view of the engineering package you're trying to put together. Those are some of the questions you ask as you're thinking about the atoms that you want. Also, is deterministic variation going to be important to you as opposed to random fluctuations? That can also impact the type of atom you want to use. Oh, without going into great detail, that's about as much as I would say right now.
Yeah, then that makes sense. And it might kind of lead into his fourth question here of what are the security risks or potential attack vectors for an atomic clock? Is there a way that you can undermine their performance?
Well, that's a question that, number one, a lot of people are interested. Number two, real answers to that is not the right forum.
Fair enough. Yes. And I'm glad. Yes. We can leave it at that.
Well, no, what I can say is the things that you would think about are, I would say, more related to the electronics because atoms, as I pointed out, are going to be relatively insensitive even to nuclear radiation. I mean, you need a heavy dose of radiation to alter the atomic properties of the atom itself.
So he's also saying that at the surface of the Earth, the gravitational field changes throughout the day, and he's wondering if that impacts the accuracy of atomic clocks. And I presume he's talking about the ground station clocks now.
Well, there is. Did he say that the Earth potential changes?
He did. He says since the gravitational field at the Earth's surface changes throughout the day.
Well, I imagine that he's talking about the moon having a gravitational effect. There's also, I mean, what's crazy is that at NIST in Boulder, what they did, now this is one of their super clocks, it's a Partington V18. What they did is they raised their atomic clock 1 inch. They moved the table up 1 inch, and they saw a change in the timekeeping by a change in the Earth's gravitational potential of 1 inch height. Now, you have, depending on how precise timekeeping you need to worry about, you do have to worry about where the clock is located on the Earth, because the Earth's gravitational potential is not spherically symmetric at all right on the Earth's surface. The other thing is people have talked, and this goes back actually to the 50s, people talked about what's called the Earth-Moon issue, and that is for the satellite in orbit, you have to worry about where the moon is. So, yes, I think one has to think about these things and in terms of the requirements that the system is asking for in terms of timekeeping.
So there are more questions from the tech, but I'm going to take advantage of my host status and ask one of my own based on that. So at the end of your discussion, you were talking about atomic clocks having reached the point where the space clock was no longer in the user error equation.
Yes.
And of course, we see development of some extremely high-end atomic clocks that are better performance than the flying ones that you were showing. I'm curious, if the atomic clocks are reaching that performance level on the space side, do you foresee a downturn in atomic clock development research and funding because this need is decreasing? Or would you say the need is not decreasing and has other use for those high-end clocks?
Well, that's a good question. First of all, we're not there yet. I mean, we've got DSAC has flown once. The pop clock has not flown. So we still have a lot of development to do to make these clocks reach those performance. The other thing I pointed out is we have no idea whether these clocks have 10, 15-year lifetime reliability. That's an open question. So I would argue that there's going to be, even after these show that they work, there's going to be a lot of effort going into making them much more reliable. In terms of better performing clocks, we're going out to the moon and Mars. And we're going to have these clocks on the surface of the moon and Mars. And the moon's surface has incredible temperature variations. I think that we're going to start seeing questions about long-term stability, long-term reliability, and I would also argue that I said you were limited by the ephemeris error. Well, once that limits you, people are going to start trying to improve the ephemeris error. And if they drop the ephemeris error, then you're going to be limited by the clock again. So I don't know that clock development is going to reach a halt. I think that there's going to be a lot of work done. I also think there's going to be a lot of work pushing these designs to smaller size, weight, and power, which from my interest in terms of atomic physics is great because that keeps me employed even into my retirement.
Well, that is, of course, a very good thing. We want to keep that going. So we do have two more questions. I know you've gone way over time with us here, and we do appreciate that. So just kind of get through these quickly. So we have, why are atomic clocks insensitive to radiation, and would cosmic rays or other charged particles impact them in space, or would they remain insensitive?
So one thing you can imagine, let's take the vapor cell clock. So I've got these atoms contained in a glass cell. And some of these atoms just, they'll sit on the surface. So if I have space radiation come in, the glass has a better chance of absorbing, let's say, gamma rays or the heavy high energy particles. And they could blow things off the surface, and they would change the environment that the rubidium atom finds itself in. That's one way. We've actually looked at that, and we don't think it's too important. But if you think about the atom itself, what would radiation have to do? Well, I mean, the vapor pressure of rubidium that we're using is, let's say, 10 to the 10th atoms per cubic centimeter. That's a pressure of 10 to the minus 6 torr. So it's a very, very not dense vapor at all. So what kind of flux of gamma rays and heavy energy particles are you going to have any kind of major absorption by this tenuous vapor? The other thing is that heavy particle has to come in and interact with the nucleus. And if it interacts with the nucleus, it's going to change the isotopic species. So that's why I say atoms are going to be relatively insensitive until you get into just incredible, high energy particle fluxes or gamma ray fluxes where you really got enough to appreciably change the nuclear properties of this 10 to the minus 5 torr vapor. Does that sort of answer that question?
I think it does. And I'm just really excited for this next question here. The last one we have, it's nice to end on a chance to speculate about some really high-end missions. So you were talking about going and trying to navigate to the moon and Mars. We have a question here that says, what sort of stability and accuracy levels are needed for deep space autonomous navigation, such as an asteroid sampling mission or a planetary exploration mission to Jupiter's moons? And how far are we from achieving those accuracy levels, and what are the biggest challenges?
So that's what the deep space atomic clock was designed for. The guys who built that, I know very well. John Prestige, Eric Burt, wrote a paper with Greg Weaver out of Johns Hopkins, where they pointed out that this is precisely the type of clock you would want for deep space missions. In a sense, we're there. The question is funding available to JPL to further develop this DSAC clock to reduce the size, weight, and performance, have long-term reliability, so that it can be commercial off the shelf available for these deep space exploration missions. So I think we're there with the technology. It's just now transitioning that technology into devices that could be more readily employed in the space missions.
Right. Well, that is I think, a very exciting and good place to call it to a close. This is a Quantum for National Security TAC, so the people in the TAC can go advocate for funding like that on all of our behalves. So I want to say thank you again to Dr. Camparo. I think the TAC really appreciates him coming to speak today. And a reminder to everyone else that we will be picking up the TAC lecture series with inertial sensors in August. Again, thank you, Dr. Camparo, and we will go ahead and end the meeting there.
My pleasure. Have a good day, everybody.